is Indrajit WADGAONKAR with the topic Breaking the Wall of Quantum Mechanical Analysis. Indrajit, please. Indrajit, you're on mute.
Can I start again, please?
Yes, okay, start from the beginning. Yeah, please move to the first slide.
Sorry. Okay, I'm ready.
Okay, Indrajit, please start.
So what is so critical about quantum mechanical analysis of a system? The governing equation is right here. Looks simple and benign, right? But let me tell you that this equation involves the position and momentum of every single electron in the system. And there are 10 to the power 23 electrons. Now let that sink in for a moment. If I have to only store these many numbers in a computer, I would require some billions of terabytes of memory. And then to write functions of these many numbers and to see how that function changes in time, that's a nightmare. It is beyond our supercomputers. Now, quantum computers might have a chance. But then the issue is, to build efficient quantum computers, you need quantum mechanical analysis, for which you need efficient quantum computers. When things start to look so ominous, I prefer to go back to my PhD training and ask the most relevant question: is this even worth doing? So let's take one example. Just recently, Google announced that a particular task, which would have taken 10,000 years on the world's fastest supercomputer, was accomplished on their experimental quantum computer in a matter of 200 seconds. Now imagine the kind of impact these computers can have on something like vaccine development. In fact, how many lives we could have saved this pandemic if our supercomputers helped us build reliable vaccine in a matter of days instead of years. And quantum computers is just one of the applications that lie beyond the wall of quantum mechanical analysis. So in my PhD, I am taking a small but decisive step to bring down this wall. We use something called as a time-dependent Boltzmann equation to analyze quantum systems. The right-hand side of this equation is the collision integral term, and the solution to just this one term is beyond practical limits. And there are two reasons. First is, even for simpler systems, the computational cost is enormous. And second is, the currently available methods do not conserve critical quantities like energy. So we have developed a solver which conserves critical quantities like energy, but more importantly, the gain in the computational cost is significant. Here on the top is the computational cost for other available solvers, and on the bottom is the computational cost for our solver. And this drastic improvement in the computational cost has already allowed us to apply our solver to a host of quantum systems. For example, here on the left, you see the simulations from thermalization of how electrons go back to equilibrium after an excitation in doped graphene. It's the first time that we were able to actually probe deeper in the underlying mechanisms and look at these intricate details, visualize them. And it keeps on getting interesting from here on. In fact, for other systems like topological insulators and carbon nanotubes, we have been able to predict beforehand the dominant mechanisms. In the future, for example, spintronics and ultrafast thermalization might revolutionize technology, and our solver can be used to do that. So in summary, we are at the threshold of technological evolution, and my work is a step forward to it. Thank you.
Thank you.